So we've proved Sylow's second theorem that says that if you have two Sylow P subgroups, then they're conjugate. They're conjugate. Let's see what that means with an example. Let's do again our example of D6. D6 has three subgroups of size 4. So there's subgroup P1, generated by alpha and rho cubed. Again, I'm thinking of the hexagon, and I'm thinking rho is a clockwise rotation, and alpha is a reflection about some axis. This is the subgroup containing 1 alpha rho cubed and alpha rho cubed. There's P2, generated by alpha rho and rho cubed. This is the subgroup containing 1 alpha rho, rho cubed, and alpha rho to the 4th. And lastly, there's P3, generated by alpha rho squared and rho cubed. This is 1 alpha rho squared, rho cubed, and alpha rho to the 5th. So here are my three Sylow 2 subgroups of D6. And I'm just going to show you that if you did the direct calculations, you could find these two facts. Alpha rho squared inverse, P1, alpha rho squared. That means you take every element in P1 and multiply these things out. It turns out that you will get the elements in P2. You won't necessarily get them in the order listed, but you'll get all the elements in P2. In fact, if you did the multiplication here of the elements in P1, the order that you would find is 1 alpha rho to the 4th, rho cubed, and alpha rho. But it's still the same set as P2. And similarly, if you did the direct calculations, you could turn P1 into P3. I'm going to leave it for you. It's probably a good exercise to find the element in the group D6 that can turn P2 into P3. So can you do this? Can you do this? Can you find an A that turns P2 into P3 with conjugation? That'd be a good thing to practice with. But this does show that P1, one of the Sylow 2 subgroups, can be turned into any of the other two with this conjugation operation. So that's an example of what Sylow's second theorem is saying.